All right, can I have everyone's attention? I'd like to introduce our speaker today. This is Shaun Stewart. He is from Intuitive Machines, and you guys have met a couple other people from there. I guess he's recently been on a world tour. Today he's going to be talking about using physics and video game technology to build a commercial drilling training simulator. And just a little bit of background on Shaun. He is a senior development engineer at Intuitive Machines here in Houston. He received his bachelor's and master's degrees in aerospace engineering from the University of Texas at Austin in 2004. For approximately 10 years, he's been working at NASA modeling spacecraft navigation systems, testing and developing navigation flight software, and simulated flight environments for manned spaceflight. Since joining Intuitive Machines in 2014, he's enjoyed applying skills and techniques for physics modeling and simulation used at NASA to problems pertinent to the oil and gas industry on Earth. So, it seems to be an exciting talk. I'll hand it over to Shaun.
Thank you, Dr. Garrison. Good evening, everybody. Yeah, as Dr. Garrison said, I just got back from Canada. We were doing some helicopter testing with some Doppler LiDAR technology that we're trying to develop for survey in Antarctica. And so that's kind of another project that maybe we'll have a chance to talk about next year. So for those of you that were here prior 2 weeks, my colleagues gave presentations on work that we've done, capping stack work on the subsea floor 2 weeks ago, and Tim Crane gave a talk last week about our reentry vehicle technology for returning vehicles from the International Space Station to the Earth. And today I'm going to talk about technology that we've taken basically from our experience at building training simulators for astronauts at NASA, and trying to apply that to make that a capability of use for the oil and gas industry. And specifically with respect to horizontal directional drilling. And so this is a little different than drilling for oil. This is basically companies that run, for example, river crossings to install drain systems, water conduit, electrical conduit, approximately 100 feet under the ground, mile to 2 miles, 3 to 5 miles from entry to exit. And so it's a much more precise operation than simply just trying to hit a reservoir of oil into the ground. And so they're basically trying to stay within accuracy of matter of feet, drilling 1.5 miles away, only looking at basically the pressure gauges and some survey data that they have available to them on their equipment. So I'm going to give kind of some background into Intuitive Machines and work that we've done that's pertinent to this technology, and then kind of give an overview of the problem of horizontal directional drilling, and then talk about our solution for basically allowing drillers to practice this operation in a simulated environment in real time. And then finally, I'll open up to questions if there are any questions. And so essentially what we're talking about is real-time software working with hardware in the loop, with humans in the loop, interacting with the system, and it's a safety-critical system. And so it's very imperative that any failure in this system can be catastrophic, whether in this case to the oil and gas industry, not only for they're essentially trying to make money in doing this job effectively and efficiently, but you also have machinery, and there's a group of 10 to 12 people who are operating, have hands on this machine, that if something goes wrong, could cause significant damage or seriously hurt someone. And so the way someone becomes a driller today is they basically get hired and they observe the operation for 2 years. And after some time, they get some matter of minutes on the equipment, and over the years, they develop enough confidence that they actually let someone become a driller, and that's sort of the process today. So we're looking to basically take technologies that we developed for, this is a picture of the Orion. It's a cockpit simulator that the astronauts use to basically run the Orion flight software through entry and orbit cislunar scenarios. Running the flight software and looking at displays that they're going to see when they get in space, and operating with controls with the actual controls, hardware in the loop, running the sim in real time. So thank you. And so this is in Building 4 on site at JSC. And that's running in coordination with, basically they have in the back room a mission control. They're running flight software on the flight computer. It's driving the displays and the telemetry parameters that the astronauts are seeing. And we're able to run through all sorts of scenarios in practice and issue faults and see if there are all these different scenarios that the astronauts on board and the ground control crew on the ground understand and are able to interact and handle any issues that may occur. And so that's essentially a good analog to exactly what we're trying to do for this problem. And so here, just to give you a sense of scale. This is a drilling rig, and it can pull a force of 1.3 million pounds. And so the way a job works is, this is one example where they basically do a pilot hole from one end, and they're doing a river crossing in this case. They have precise requirements of the depth at which they need to cross underneath this river, and then come out, and there's a specific point on the other side they're trying to exit. The length from entry to exit can be anywhere from 800 feet to 3,000 or 6,000 to 3 or 4 miles. And for distances over 2 miles, they generally have 2 rigs. They'll have one entry point on both ends, and they will meet in the middle and bump bits in the middle, and then pull the bit through, and then finish the hole, pull the pipe through. And the pipe diameter can be in excess of 60 inches in diameter. And so you can imagine how much energy it would take to drag a pipe, a 60-inch pipe, through a hole 2 miles long. And so there's enormous stresses that are in the system when they're drilling, and then you have people that are basically working right there on the rig with every joint. And so accidents can and do happen, and so we're basically trying to improve the operation, not only in just execution of the hole, the performance of the hole, but also in educating the driller of what to expect when interacting with other people on the rig. Another complexity, this is basically a CAD model of the bottom hole assembly, which is, this is the final, on the very end of the pipe, there's a 30-foot non-magnetic drill collar. And then on the other side of this, you've got hundreds of just standard drill pipe that are approximately 30 feet long. And the reason this is a non-magnetic is that you have a sensor pack that's right here where the steel pipe can interfere, and so they basically have this special drill collar so they can get good data to accurately know where they are underground. And then the way they steer is this. You can't tell on this scale, but there's a slight bend in this piece, and so they basically can orient that bend. If they orient it up and they push, then when they're drilling, they're basically going to climb and build angle. And they have the ability on their gauges to know how that bit is oriented underground, however far away. And so this equipment here, in this scenario, this is basically a fixed piece of equipment that they would use in drilling in sand, for example, in a jetting. So they basically have a jet, and force about 300 gallons per minute of drilling fluid out of this hole, and it blows out the formation in front, and then the debris gets circulated behind the drill pipe. When they're drilling through rock, there's a slightly different configuration, which they use a mud motor, where this is basically a stator, and there's a rotor piece that they force mud through the rotor, and it forces this drill bit to spin. And that piece is 30 feet long, and then the probe is back in this area. And so whenever they're drilling in rock and they make a mistake, for example, and the rate of penetration can be 10 feet an hour or more or less. And if you get off course, basically you've drilled 30 feet past where you're trying to be before you know that you're off. And then you have to pull this out and try and correct in hard rock. And so it's really important that they're able to have sort of a sense of, by looking at the measurements in any given configuration that they're getting, that they understand that this is back away from where they're actually working, and that it may take them some time to be able to realize how bad they're actually off right now. So basically the problem is to build a simulation where we're modeling in real time the physics of drilling through rock and sand using this type of equipment. And we're interested in modeling the orientation of this bit so that you can know if you're pushing, which way you expect to go. Also, we're basically modeling as a function of how fast you push, how hard you push, and the amount of the volume of mud that you're circulating and the type of rock that you're drilling in. What's your rate of penetration that you expect to see? And then if your rate of penetration changes, do you understand why? And it can be unexpected geology or an issue with the machine. We're also modeling the dynamics of the drill string. And so we can have hundreds of these 30-foot steel drill pipe in the ground. And as stiff as they may seem, they do and will deform underground under high forces and torque. And so we're modeling and capturing the deformation of the drill pipe and the bending and twisting of that drill pipe. And it can be as much as where basically when you turn the drill at the rig, you can have as much as a degree of twist in your drill pipe for every 1,000 feet. And so it may take a while for when you turn for the actual bit to respond. And so that's why we're basically measuring the orientation of the bit right here so that they can know, even though you maybe are turning the rig up hole, your pipe down hole may not be turning at all. And so the performance of their ability to finish a hole depends on how straight it is. If you have a lot of variations, then it can be very difficult to pull a pipe through a hole that's not, it has lots of, I think the technical term is tortuosity. And so we're modeling the drill string friction. So if you're trying to push or pull or turn, basically the tortuosity of the hole will result in contact with the pipe in more or less places. And so we're basically trying to model the friction that they see when they're static, or rotating or sliding, or rotating and sliding, and getting a realistic response of what they expect to see in the field in different types of geology. Another important factor is the rate of debris generation and circulation. You're generating, as you're drilling, debris of different sizes depending on the drilling configuration and the geology. And if your mud flow rate is not appropriate, then those particles may not come back out of the hole, and it can clog the hole. And at that point, you're basically, if you create a closed volume and you're pumping high pressure fluid in that volume, and it's going to find the path of least resistance, which sometimes is straight up to the surface. And so that can cause basically a degradation in the quality of the hull, and they lose fluid, and so that's another scenario which can be catastrophic and require basically scrapping an entire project and starting over. And then finally, trying to model the characteristics of the measurements that they expect to see. All measurements are by nature imperfect, and so trying to make sure that we account for those types of sensitivities so that it gives them another kind of realistic factor to take into account. Okay. And so essentially what we've done to solve this problem, we have a horizontal directional drilling simulator, and with the ability to configure the type of rig that they're using. They have, I showed stats for the 1.3 million pound rig, but they also have a 440,000 pound rig. There's all kinds of variations depending on the size of the job. And here on the right is an example of their control panel. And so we have taken an actual control panel that was provided that they use on the job and wired it up to our simulation server so that the driller can practice with the actual hardware that they use to drive in the field. And then taking those signals and process them through a real-time analog to digital conversion of the push and pull controls and the clamps for connecting and disconnecting the pipes, controlling the mud flow rate, and looking at this, basically their pressure gauges, which tells them what's going on with the rig, and putting that into a physics model of the rig uphole and the drilling operation underground. So I'm going to go through, I think one key theme throughout the talk is that the dynamics and the physics of modeling drilling underground is very, very different than rigid body dynamics in space. And so this was a big challenge for, we extended the basic principle of development of software for hardware in the loop, real-time systems. But we had to expand our ability to model this type of physics, this type of interaction of drilling and cutting and jetting and rock, generating and circulating debris, modeling friction and deformation of miles of pipe. And so we used open source tools where needed to bring in capabilities that we did not already have to solve this problem. And so the first major piece is a multi-physics simulation and analysis engine. This is also what we use to solve the subsea, the dynamics for the subsea captain stack problem. It's a multi-body dynamics simulator. It can run, basically it's designed to model, complex machines and mechanisms. Enables us to do the dynamics and kinematics of the system using kind of an open object-oriented C++ architecture, and apply forces and torques to elements in the system, and it will solve for constraints of the system. So it is basically the validated tool that allows us to go and focus on other elements like how do we model the rate of penetration through rock, those things that we had to go do research to figure out how to model. Finite elements is another one that we knew from the start that traditional finite element methods were not fast enough to model basically the deformation of a system on this scale in real time. And so we've used a finite element analysis method from this tool that allows us to look at large deformations every time step and basically capture the expected response to a sufficient fidelity in real time. Also, it basically allows us to parallelize the problem, and so we've broken it up and basically are running this problem in parallel across 35 processors. and are using basically splitting the load, the computational load across CPUs to get this job done. And this is also made possible by this tool. And then finally, a big part of this is, they're interested in connecting pipes together and collisions underground. And so the collision models, the collision detection and handling of when you collide two pipes together, screw them together, applying large torque to make up a joint, the physics of that operation is critical. And so we're using collision detection from this tool to be able to model. And so here you can see this is a model of the deckhand, which this is just a standard excavator, but this piece right here is called the deckhand. It's a pipe gripper. It's basically a special tool that's made for this type of work. It allows them to grab a pipe and put it on the rig. And so we developed, based on CAD measurements, basically a 3D model of this machine that we're using in the simulation. And then here's just an example simulation from the tool showing the FEA, and basically this is a model of a tire rolling through granulated earth, and you can see it basically is capturing the deformation of the tire in interaction with basically a pile of particles on the ground. And so this fundamentally is capability that we need to be able to look at capturing the deformation of a 3D mesh and interactions with granular material. Okay, so basically we broke up the software problem into a multi-threaded application, and we're running natively on Windows. And that's sort of important because a lot of the tools that we pulled in, these open source tools, are being developed on Windows. Traditionally, all the work we do at NASA is done on Linux-based systems and software, or other flight critical type OSs that are not normally widely used. And so we kind of adapted and ported our development environment to Windows so that the tools that we're bringing in work well in those environments, are tested and validated in those environments. And it basically allowed us to quickly learn how to use those, run their tools, their demonstration tutorials, and pull these tools in. So we broke up the application into several threads. There's an uphole rig model, which basically is the model of all the machines that you see in this uphole graphics here. And so this is an example. This is a prime drilling 1.3 million pound rig. The clamps down on the bottom are what's used to make and break joints. This device can slide up and down on the rig rail. It's got two clamps, one that will hold the drill string fixed and another that will twist the free pipe relative to that and force them to make basically a super tight joint, so that when you have a mile of pipe underground, you happen to put a high torque, anti-torque, that you won't accidentally have a separation, half a mile, halfway down underground, and lose half your drill string. And so one thing they're really concerned with is how tightly these joints are made, every joint, and they want to make sure that the driller is aware and is making those up every time, because otherwise you can lose a whole lot of very expensive equipment underground, or have to spend a week trying to fish it out and connect to it, pull it out. This is the carriage. It's basically it slides in and allows them to bring in new pipes, and it'll connect on the spindle up top and connect to the drill string down below. And this is the deckhand gripper that I described, that is basically queuing and grabbing pipes off the stack, bringing them into the system as the driller is putting pipes in. When they're pulling pipes out, it'll grab the pipe and stack it. And so that's all basically the mechanics of all this interaction here. all the way down to 60 feet in the ground is part of this up-hole rig model. Then we have another thread which is modeling a downhole drill pipe model, and that's essentially what you see here. And you can imagine there's a control volume that ends 60 feet underground and goes all the way to the beginning of that non-magnetic drill collar. And so the deformation and the friction and everything that's happening between the rig and the drill bit is being modeled in that thread. And we have control volumes that they basically model the constraints and the interactions between those threads, and they exchange information over shared memory in real time. Then there's another thread that's basically just modeling the drilling and the orientation of the drill bit and the high pressure jets relative to the end of the borehole, basically the impingement distance between the jet, the expansion of that jet in basically a pressurized volume in front of the bit, and the impact, the impingement angle, and basically the erosion, the depth of penetration that we expect to see through jetting, through pushing and turning as it's grinding through whatever is in front. Then we have a real-time event receiver, and so this is the piece that essentially is monitoring the control panel, the hardware control panel, and we have essentially 100 signals, maybe 120, that are coming from all the different buttons and switches and controls that the driller can use, updating those to the model, the up-hole thread model, and capturing the response in closed-loop control system models that basically try and drive these carriages to the target velocities, the target forces, whatever is being commanded on the control panel. It's also used, once we kind of run the whole sim, the dynamic step, when we get the result of each step, then we take measurements of what they should expect to see on the hardware gauges and also on virtual gauges that are implemented in the graphics thread, and update the measurements that they expect to see every time step. And then finally, there is a graphics thread where we have leveraged another open source tool that's been developed. It's basically for the video game industry. It's a tool called Unreal 4. There's a couple of different platforms you can use to develop video games, and this is one of the primary ones. And it's been something of a revelation that they are really pushing the edge of what we can do with our engineering tools, and we found that by pulling in some of these capabilities that are currently being developed for video games, there's so much energy and money being put into that some of the physics that they're modeling is realistic enough. It's better than what we can do with our engineering tools in real time. And so, for example, we're modeling the fluid flow of mud. So if they have high pressure mud in the drill pipe and they break the connection with the spindle and you get this spewing of mud out of the pipe, we model that entirely using Unreal 4. Because we're not actually interested in it's not critical, the actual flow and the response of that material, but it's important for the driller to have an intuitive sense that there's a high pressure fluid there. And so the fact that they can have it impacting surfaces and having the velocity of the pressure relative response that's sufficient enough to be realistic, it's a usable capability that we've implemented. There's also a downhole. This is a little more detail about the drilling and jetting model. We used another open source tool that's developed by DreamWorks Animation called OpenBDB. And BDB stands for voxel database. And it's basically, it's a tool for manipulation of sparse volumetric data. And so one example is when we're trying to capture the geology of the ground that we're trying to drill through. It's sort of this infinite volume of earth that we want to interact with. This kind of shows you how it efficiently captures that information with the minimum amount of data. And so for this volume here, where you have a uniform density of rock, it's one big volume that they use to capture basically the properties of this entire space. And then in this area where you have more detail, they break it up automatically into smaller voxels to be able to capture efficiently the data that's needed to represent the state of that system. And so we use this OpenVDB tool to capture the geology of the Earth that we're drilling in. And also when we're generating a borehole, we capture in real time the generation of that space. And here we can, this is obviously not realistic, but it's just to demonstrate that as we're drilling, we basically generate we capture sort of the delta space that's interacted as a function of our erosion model, and it generates a voxelized space that's sufficient to capture these points that are necessary to define the borehole. And then we can take these points, and it has a function to create a level set, and we create basically a 3D model that we can use to capture, and this is in turn then part of the boundary condition that's passed into the Drillstring model for computing the friction of the entire Drillstring for the history of the drilled hole, so that we can look at how tortuous this hole is and see what force it would take to pull a pipe through that, or if the pipe would fail long before you ever had any chance of sliding something through that system. And so this is an example of a drilled hole that we did with the drilling simulator, and you can see the size of the voxels here and the detail that it breaks it down to capture that, basically the boundary of the hole as we're drilling. And so this works amazingly quickly, and so that was just a capability that's out there for the movie industry that we were able to pick up and use in a matter of weeks. And I mentioned earlier the Drillstring dynamics model. So we model each pipe using an FEA method called the ANCF, or Absolute Nodal Coordinate Frame method. And basically it's a nonlinear finite element analysis method that allows us to have large elements and so we break up the pipes into 3 or 4 elements, 10-foot segments essentially that can deform and have significant deformations at a time step that are semi-realistic. And so by doing this and using this method, it allows us to model the deformation of these pipes in real time and capture an expected response. So the ANCF method will capture bending in 2 dimensions, so say vertically and laterally. And then we have, in between 2 segments, we've incorporated a torsional spring in each pipe that will allow us to account for the torsional deformation that we expect to see. And then calibrating and tuning the constants for those models and the springs and dampers that represent it. Basically, we use data from the field to kind of calibrate the expected response. I have some videos here that are kind of representative of that. Let me pull those up real quick. So let me pause this. How do I pause this? And so this is, you're kind of viewing under the covers here. We're looking at our simplified, model of what's underneath the graphics. And so this is just a block that represents the carriage and the spindle on the rail, and we have our inclined rig here, and this is a system of wrenches. And so here we have a pipe in the deckhand that's sort of waiting to be added, and there's one in the rig that's connected to the spindle. And so we're able to connect the spindle to that free pipe. We drill it down and push it through down in the hole. Unscrew, we clamp with a clamp, unscrew that spindle, and then pull the next pipe in and continue. And so here you can see, I think we're basically tightening that joint together and then sliding both pipes in the ground. Here's an illustration of basically this is for a single 30-foot pipe where we've broken it up into segments, A and CF elements here with the blue and white cylinders essentially. And then we've implemented a torsional segment here so we can capture torsional deformation of that individual pipe. And then we connect these system of pipes together, and we're able to capture accumulated effects of high forces and torques on a system on a drill string. So that's kind of the 1D bending, and I think we also get a little, no, that's how we get it. Okay. All right, here, this is interesting. And so for a driller, the operation of connecting two pipes together is of critical importance. And so spent a lot of time on trying to figure out how to accurately model the physics involved in screwing two pipes together. So you have the pin on one pipe and the box of another, and if you slam them together, then there's going to be a collision. And in order for you to screw those, there has to be basically relative rotation, and the relative translation of those two pipes is sort of constrained by the pitch of the screw. And so here, this is sort of a demonstration of two pipes. So we slam them together, and then as you rotate, they're able to pull together until finally they're fully screwed together. And then after they're face up, then what's of critical importance is how tightly those joints are torqued together after they can no longer be screwed any longer. And then if you have a pipe that's made up, then it takes a sufficient torque to break that joint. And once it's broken, then you can't separate them without unscrewing them. And then there's two free pipes that can be collided again. And so there's several states of collision and constrained motion throughout all of that that's critical importance. And we do all of that with this simulation engine that we use to model the drill string. And so here is kind of an early accumulated drill string, looking at trying to calibrate the nature of these elements and the springs that connect them, and looking at expected response at the end of miles of drill pipe and calibrating this to expectation. All right. I start. Where's the? There we go. Okay. And so here is a picture of the hardware control panel. And so there's controls for the engine. This is control for the carriage and the rotary, and this is controls for the wrenches. There's a fixed wrench and there's a fixed clamp and a wrench clamp, and then they also have a clamp up top. And then there's all types of kind of presets that they can use to make sure that they don't exceed a limit in terms of the maximum torque or force that they want to apply. And then these are the hardware gauges that we use so they can look at the amount of PSI that they're putting into the hydraulic system that they're seeing as they're working. In addition, there's an external mud pump control. This term basically controls how many gallons per minute of drilling mud are being forced through the drill string. And then this is a virtual gauge that we developed that tells them the inclination and azimuth and tool face angle, which is essentially the orientation of the drill bit relative to up. And it's in addition to some other things about pressures and temperatures that are being recorded underground. And so we have a system of analog to digital converters. I talked about this already, but just for completion. So we pull wires from this system into the ADD converters. We're monitoring those at high rate, real time, and capturing the states of this entire system, putting it in shared memory that is basically being sampled by the uphole model, every time it runs a cycle. So these things they're essentially asynchronous, where the event receiver is running as fast as it can all the time, updating the current state of this at 100 hertz or 200 hertz, and then we're running our dynamics probably 10 hertz in terms of what the entire cycle of what's happening. For the 3D graphics and the modeling of this system, a lot of this was interesting because what the rig is and how it works, a lot of that information is proprietary. And so we had to sort of surmise from available CAD of the rig that's provided, as just kind of open knowledge, videos of the rig in operation, and implementing sort of 3D models of this system in CAD. This is done in another open source tool called Blender for modeling the deckhand pipe gripper that they use in this job. And so building scaled 3D models of all this equipment and modeling the hydraulic controllers that drive the carriage and the wrenches and basically give outputs to the pressure gauges that tell them what's going on with the equipment. And so that was a large part of this work, is sort of trying to understand what the system is, how it works, and how to model it. And at the end, here's essentially what we developed. So here you can see, this is our customer. This is what they normally see, and I think the reality is a lot messier than our kind of clean graphics picture here of the world. But they're able to sit down at the actual control panel that they use in the field and run and drive and look at basically a simulated view of what they expect to see when working on a job. And this enables them to train and evaluate if a driller's ability and performance to execute a plan effectively. And also, they're able to throw in safety issues or issues with the rig and make sure that the driller can recognize that there's a problem and respond to it appropriately. So, in summary, what we've done, we've basically pulled on our expertise from working in the aerospace industry and applied that to the oil and gas industry. And we've done that by leveraging tools that are, outside of our experience, even outside of our industry, and found capabilities that are developed for the gaming industry, for the movie industry, that are relevant to high fidelity engineering analysis, modeling, and simulation, and really enable us to solve a problem that we otherwise would not have been able to solve. The ability to model this system in real time was a significant challenge, and without sort of advances in capability that are being moved forward through these other industries, I'm not sure that it would be possible for us to solve this. All right. So they're using a magnetometer underground to detect the magnetic field when they're heading, and so they have, basically a survey of the expected magnetics in the ground before they start the job, and they're using that to navigate while they're drilling. And so they have basically a wired sensor that runs all the way uphole to the rig, and they're getting real-time data from the magnetometer underground. And they have a gyro as well that gives them orientation of the drill bit. Okay. Do you have a question?
Yeah, I was just curious, because I'm unfamiliar with this, but assuming you do most of your training front-end loaded before you start drilling, you have some continuous level of training while you're going. What percentage of the total project of drilling this materials with pipes and everything is the training aspect? Approximately, how does that work?
Well, I get to go and observe on a few jobs, and I think it can take the operation of drilling. They have sort of a couple of phases of a project, which is drilling the pilot hole, and in this case they have essentially a 9-inch bit and make a 9-inch hole, and then they have to come back and increase the diameter of the hole. I call it reaming. So if you increase it to 15, 20, 60 inches, whatever, they have a reamer that they have to run through there, and it just basically widens the existing hole. So drilling the pilot hole is really I think their expert challenge. And so they have some ability during the reaming operation to allow someone who's inexperienced to come in and practice for a couple of segments. And then once the hole is finished, they run a swab through the hole to kind of clean it, and then the final phase is pulling through the finished pipe through the entire hole. And so they'll assemble the entire pipe above ground, miles long, and then drag it into the hole once it's finished. I get to go see a job in South Carolina where there was an issue that there was an overpressure vent in front. They weren't basically properly cleaning the hole, and so they were fracking out all along the way. And then they finished the hole finally after lots of issues and trouble. And during pulling the pipe about halfway through, the pipe broke. And so then they had to start over. And yeah, I think the cost of that, I think it was about $2 million to start over. So certainly, I think it's I think the way that things are done now is kind of fast and loose, where they do take time to train people up, but I think things are allowed to happen, and they worry about how to fix them after the fact.
So this is all the transport, right? That's training to transport fuels and oils.
This is it could be for sewage or electrical or water and all kinds of. It's not necessarily for oil and gas. So there is kind of an analog to this directional drilling for oil and gas, where it's more like incline drilling. This is literally horizontal drilling. So it's a big stress on the drill pipe because the entire length is laying on its side in the ground, so you have a lot more friction. Versus if you're drilling vertically, most of that is allowed to spin. A lot of times, like the one I went to was a protected marsh, and so they had to drill under it. Rivers. Well, you can go hundreds of feet underground and not affect the environment there. Unless you start fracking. Yeah. Yeah. Yeah, that's why I want to make sure it's done right. But I think that's an appropriate observation that sometimes mistakes can be catastrophic. Not only to the bottom line, but also to the environment that you're working in. We're mainly focused on just trying to model the physics of what happens in varied geology, and their customers sort of taking this and developing a training program and integrating with their operations. So we're not really involved with that aspect. Yeah.
So the choice to use a gaming engine to basically drive your simulation, were there people that working with that in the past that kind of led to that, or like how that decision made? Because it seems to be an interesting choice if you're not in gaming or not, necessarily doing. Because I mean, in the time, I'm pretty sure other people were using other simulation packages and software, but to decide, oh well, this does what I want to do, it does as well. Like how was that discovered?
Yeah, and so we have, part of our research and development group, we have some effort, some time that we spend in evaluating new tools and new capabilities. And so those things that we do in advance of, and so before, there is a lot of risk in pulling in, open source tools into your product line. And so we have, a process for evaluating those things using build robots and automated test, running, basically making sure that the tool always works as we expect and before we try and use it in a product. And so, but because the user base for these things are so enormous, there's lots of tools, lots of resources out there for solving issues, lots of people that you can talk to get help. And so it can be a significant leg up. Whereas, for high fidelity modeling of the gravity of Jupiter and Mercury as we're flying an interplanetary trajectory, we have tools that are developed by NASA. It has a user base of maybe 200 people. And so getting support for that can be challenging especially if you find a problem that no one's ever seen before.
It makes sense since people have been using gaming hardware for doing these high performance simulations, so why not?
For sure. It makes sense. It's like, oh, my NVIDIA graphics card matches up with this Unreal Engine.
So yeah, actually, it's the PhysX has a Flex engine that integrates well with the Unreal Engine 4, and that PhysX engine is really what drives the fluid flow interaction that we're using to capture the mud dynamics up whole.
Any other questions? All right, let's thank our speaker. Also going to remind you guys, next week's talk, we're going to have Georgina Kramer from LPI is going to be here talking about, I think it's weather on the moon. So I guess I'll see you guys next week, and if I haven't gotten your papers from last week or anything, let me know. Also, I checked with the grad students on your project.